Hello again. Today we're going to learn how to solve complicated dynamics problems using a moving reference frame. So this will allow us to break a complicated problem into a bunch of simpler ones. We all do this every day without really thinking about it. For example, we on the Earth might, say, track the position of a satellite, and we would describe the motion of the satellite relative to us, relative to what we see. So, if this satellite had a parabolic path around the Earth or something, or elliptical path around the Earth, we could easily write that and tell how the satellite's moving relative to us. And when we do that, we don't worry about the fact that the Earth itself is actually spinning through space around the sun, and the sun is actually moving through space, I'll just draw it this way, around the center of its galaxy, and on and on and on as you go outward. So we simplify the problem down by talking about how the satellite moves relative to us. But we know that if we're moving, we could probably find a way to account for that and add that to the motion of the satellite. And that's the basic idea behind moving reference frames. If we were just talking about a point and linear velocity, then it's easy addition. When we allow the moving reference frames to rotate relative to each other, so if we defined, an x and a y here, and we allow that to rotate relative, say, to the sun's xy coordinates, then we need to have some extra terms. And this all follows pretty easily from the concept of a derivative of a vector that we've already talked about. Remember, if we take the derivative of a vector, we just take the derivative of the amplitude part, leaving the unit vectors fixed. And then this term is the derivative of the unit vector, and then we multiply by the amplitude. Another way we've written this is as A times omega cross EA. For a scalar A, that works just fine. So, in any event, we can use this same idea to derive the motion using a moving reference frame. Alright, so we can do this with a Cartesian reference frame. One example here, a really simple one. Suppose the origin is fixed and we just have a reference frame xyz that's rotating with an angular velocity omega. So this picture is kind of trying to show how the coordinate system is spinning in an absolute sense due to its angular velocity omega. And if we described the velocity of a point, or the motion of a point, with components ax, ay, az, where each of these is a function of time, then to take the derivative, we would just take the derivative of each of those functions, and then the omega cross a would account for that correction vector. So this is just an example of like what we had on the previous slide. Let's make that a little more concrete now. So let's suppose we have a reference frame, a fixed reference frame, capital X, capital Y, capital Z. And from that we have some other reference frame. And I'm just going to kind of draw a simple rotation about the z-axis, but we could have any rotation. And we call the origin of that reference frame O prime. And then relative to that reference frame, somewhere is a point P that we're really interested in. Maybe that's the motion of our satellite or something. So we could write the position of point P, the total position, or at least total in that it's kind of relative to this origin over here. That would just be the position of the origin relative to, let's use the Ginzburg notation and always use 0. So this is P relative to O. So it's just the sum of these two vectors. P relative to O is the vector from O to O prime, and then the vector from O prime to P, right? So if we want the velocity of point P, and now we tend to drop the O, Ginzburg drops the O because it's kind of just implied that there's some reference frame that this is relative to. It would be just the combination of these two vectors. Now this first one is easy because this fixed coordinate system is not rotating, so it's just simply the derivative of r. The derivative of r is just velocity. It's just the velocity of that point. But we said that our coordinate system there could rotate, so to take the derivative of this, we'll need to use the trick on the previous slide. So this, we have to have the derivative that we would see if we were sitting on the xyz frame. So Ginzburg uses this to denote the velocity as seen from the xyz reference frame. And that's what we were getting at in those previous two examples. It's the derivative when we hold the unit vectors constant. With I, j, k being constant unit vectors. So those are equivalent statements. Okay, so then we have that, and we know that if we do that, then we're also going to have to add in a correction term, which is omega cross rp o prime. And the important thing here is that omega is the angular velocity of the xyz reference frame. Alright, so that's the velocity, and this is an equation that we're going to use a lot. And if we take one more derivative, we could also get the acceleration. So the acceleration of point P would be the acceleration of point O prime. Then we have this second term, this relative term. We need to take the derivative of that. So we take the derivative holding the unit vectors constant again. So this is the derivative we would see if the unit vectors weren't moving. But we know that we're going to need a correction factor similar to what we needed up here. So we also include omega cross Vp relative to xyz. And now we need the derivative of the last term. So we need omega dot cross rpo prime. And then the derivative of that second part. And the derivative of that second part is what gave us both of these terms. So we can write the derivative of the second part as just Vp relative to x, y, z plus omega cross rp with respect to O prime. And then in the book, we'll use this a lot, so we give that a special symbol. We call that alpha. That's the angular acceleration. And you learned how to find those in a previous homework assignment. Alright, so that is the equation for the acceleration of a point. Notice this shows up twice. we combine those into a term 2 omega across Vp relative to xyz. Oops. Lost it here. 2 omega across Vp relative to xyz. This is called Coriolis acceleration, and we'll talk about that later. There's also a term omega cross Rp O prime. That term is also special. Sorry, this keeps wanting to advance slides on me. And let's actually just talk about this term really quickly. If we had some position vector Rpo prime, and let's say we just had a simple rotation out of the page, for the first one, we'll use the right-hand rule. So hopefully you can see me all right here. We have omega out of the page, so I want to point my fingers I want to curl my fingers from the direction of omega towards Rp. So hopefully you can kind of see that if I do that, my fingers start upward and they're going that way. And the only way that can happen with the right hand is if the thumb is pointing straight towards you. So let's flip back and let's see that again. So again, if the fingers, if my fingers are pointed this way and I want to curl them towards Rpo prime, then the thumb has to point that way. So this would be omega cross Rpo prime. Sorry, I don't know why this is possessed today. And if we do that one more time, we do the right-hand rule. With this, omega is once again upward, and so we have fingers this way and we're crossing them that way. We can see that the thumb has to point that way. So what we get in the end, if we had Rpo prime this way, then we'll have that derivative will be a vector pointing this way. So it's in the opposite of the radial direction. So all of that is just to show that this is the minus omega squared r term that you're used to from dynamics. All right. So we've made sense of all of these terms. I guess I should also say that this term here, alpha is the derivative of omega, so in terms of 2D dynamics, this is the theta double dot r term that you're used to from 2D dynamics. Okay, so we're going to see those equations a lot. Here they are in a neater form. And one thing that everyone always messes up is they forget that omega is the angular velocity of the moving reference frame. You're the one who will pick what the moving reference frame is. You need to pick omega to be consistent with that. And there might be lots of other omegas in the problem that will confuse you. So you need to keep that in mind. Lots of moving parts, and each one has its own angular velocity. All right. Let's do an example now, and we're going to do an example that's almost trivial. This will be kind of like shooting ducks with cannons, but it will kind of help to illustrate the process on about the simplest problem you can have. So say we want to compute the derivative of this vector A right here. where A is a constant vector, we have a constant L along the fixed I direction. So if we do that the simple way, A dot will be L dot I plus L I dot. And if the length is constant, this term is 0, and since the fixed unit vector is constant, that term is 0. So basically, using a fixed reference frame, we get that A dots obviously equal to 0. All right? Okay, so that's the answer, but let's do it using a moving reference frame, just so you can have practice with the process on a really easy problem. So, A, that's like our position vector, right? That's the position of point P. So what this is really asking for us for is, what is the velocity of point P? So let's just use our equation. So we have the motion of the reference frame, and then we're going to have the relative motion, and then we'll have omega across RP O prime. So we'll put O prime right there. So the origin is not moving, the reference frame is just spinning, not moving. Right? How is the reference frame spinning? Well, we just have omega, an omega outward. So we could say omega is theta dot in the capital K, or we could also write that as theta dot in the little k. Either of those would be valid ways to write that. And our position vector we need in the moving reference frame. So in the moving reference frame, to get to this point P over here, we need to go this way. This would be an L cosine theta along the x-axis. Then we also need to move an L sine theta. And notice this is in the negative y direction. So this would be L cosine theta in the little I minus L sine theta in the little j. Alright, so that takes care of the last term. What about the velocity relative to x, y, z? For that one, we have to put ourselves on the moving reference frame and kind of imagine what's happening. But we can use our polar coordinates. If we were sitting on the moving reference frame, then point P, we would always have a radius r, or length P would always be a length L from us. And so we could say that the position vector was L in the ER direction. And because L is constant, if we use the polar coordinates, the motion would just be L theta dot in the E theta direction. So if we were sitting on that moving reference frame, the point would seem to be moving this way. So that's our E theta direction. It would seem to be moving in the opposite of the direction that we are rotating. So, and that's actually the j direction. So this would be L theta dot capital J. At all times, that'll be the direction that it moves. And so we can say that Vp relative to x, y, z is L theta dot. And what is the capital J direction? We can break that into components. We get a cosine, this angle's theta, so we get a cosine theta in the J, a sine theta in the positive x. So this would be, let's write those in order, I guess. Sine theta in the I direction, plus cosine theta in the j direction. Alright, so if we put all of this together, Vp is equal to that term right there, plus omega theta dot k crossed into this. Let's work that out over here. So omega cross rpo prime, that's equal to theta dot in the k crossed into this vector L cosine theta I minus L sine theta j. And I like to work out these components using, or the cross product by components. So the way I do that is draw myself a little coordinate system, I, j, k, and then k crossed into I, that would be fingers this way, curling that way. So that tells me k cross I is j. And k crossed into j, again, fingers up in the k direction, curling, we get a thumb this way. So this would be k cross j. And this would be k cross I. So k cross j is a minus I. K cross I is just a j. So anyway, that will give us also an L theta dot. And let's see, k cross j was the minus I, so we get a minus L, or sorry, a minus sine theta in the I. K cross I is j, so we get a plus, wait, let's see, k cross I is j, we get a plus cosine theta in the j, and so the answer is the sum of these two terms, which should add to 0. Oh, missed a dot there. Should add to 0, but somewhere I've made a sign error and I've got a minus sign. So, let's see. The j, k cross j. Oh, this one had a minus on it, so that minus should have canceled. And, yep, okay, here's the problem. And then this should have been in the minus j direction, so we should have had a minus sign right there. So if we were doing this live, you would have helped me catch that a long time ago. But anyway, so now we have a minus and a plus, now everything works out, and all of that to show that the velocity is 0. So we really did shoot ducks with cannons on that one, right? But hopefully that shows you how you go through all of the steps that you need to work out one of these problems. Alright, let's mention one other thing, and we'll save the other examples for another video. Let's suppose the vector you want to take the derivative of is the angular velocity vector. What will you get when you do that? Well, we get that the derivative of that is omega dot plus omega cross omega, right? And this term always has to be 0. So this, though, would be the omega dot holding xyz constant, or omega dot in the relative frame. So in other words, it says that the derivative of omega, the total angular velocity, or alpha, is the same as if we took the angular velocity relative to the xyz coordinate frame. So one way of writing this is saying, the total derivative, or this is what the Ginzburg book is going to call alpha, that's equal to the relative angular velocity. So this is kind of like our omega dot relative to xyz, using that notation. So because of this, lots of interesting and sometimes strange things that can happen. You can do something wrong and still get a right answer. I guess not necessarily wrong, but you can not really follow the usual recommended form and get a right answer. So we won't talk about this a lot because it gets into some subtleties and things. But it is something interesting to be aware of, and there are occasions where we can use that trick to make a problem a little simpler. But what does this mean anyway? Well, suppose we had some omega vector, right, so that all of these coordinate axes were rotating due to that omega, right? It's hard to draw a really good 3D picture of that, but everything is spinning about this point. So the motion of the reference frame is going to affect every point in the coordinate space except the points along this line. Because any point along this line, the coordinate system is just spinning about us, right? So all of those problems, all of those points will not be affected by the rotation of the reference frame. So this kind of gives you some graphical idea of what an omega vector does, right? It's causing everything to spin about it. But any vector parallel to omega is kind of immune from that. And that's what the cross product is taking care of for us. Okay. We'll call that quits then for today, and in the next video we'll pick up with some other examples.